Welcome to section 1.3, graphs for quantitative data. In this section, we'll focus on how to visualize numerical data to uncover patterns, spot unusual values, and prepare for deeper statistical analysis. Quantitative data measures amounts or counts. It allows us to answer questions like how much, how long, or how many. These variables can be either discrete or continuous. Discrete variables are countables and take whole number values, like the number of siblings you have. Continuous variables can take on any value within a range and are measured, not counted, like weight, height, or time. When we graph these values, we often want to look for patterns in how they behave. Are they clustered in one area? Are they spread out? Are there unusual values? The graph helps us answer those questions visually. Histograms are the go-to tool for visualizing quantitative data. They show how many values fall into different ranges, which we call bins or intervals. Unlike bar graphs for categorical data, the bars in a histogram touch each other. That's because the data represents a continuous range of numbers. One bin flows into the next without gaps. In a bar graph, each category is separate and distinct, like types of fruit or favorite colors, so the bars are spaced out. In contrast, a histogram for something like exam scores will group all the scores from, say, 60 to 69 into one bar, then 70 to 79 in another bar, and so on. The height of the bar tells you how many values fall into that range. This lets you see the shape of the data, where it peaks, where it tapers off, and how spread out it is. Dot plots are simple but powerful. They're great for small data sets and offer a clear visual of the actual values. Each dot represents one data point. And if multiple data points have the same value, the dots are stacked. To interpret a dot plot, look for clusters or areas where many dots are stacked or bunched together. These represent values that appear frequently. Gaps are places along the axis where there are no dots at all, signaling ranges with no observations. Outliers are dots that stand alone, far from the cluster of the rest of the data. For example, if most dots are between 60 and 80 on a test score scale, but one dot is at 30, that value is an outlier. Dot plots make it easy to visually assess center, spread, and unusual points without requiring any calculations. By the way, the graph that you're looking at on the screen is a scatter plot, not a dot plot, okay? Now, this scatter plot I picked because somebody already made it, and it easily shows like clusters and outliers. A dot plot is just a horizontal axis like so. And let's say that we're arranging, values, I don't know, this might be 8, if it'll draw, but it won't. There we go. 8, 9, 10. And I would just set the dot on the value. So if I have 3 8s, I'd put 1, 2, 3 dots above 8. That should be 3 dots. If I have 5 dots above, if I have 5 data points that are 9, I'd do 1, 2, 3, 4, 5 data points above 9, and so on. So in other words, a dot plot kind of looks like a histogram, only it's just dots stacked above the values. Line charts are used when data are collected over time. This kind of data is called a time series. For example, monthly sales revenue, weekly temperatures, or yearly population counts are all time series. In a line chart, time is always on the horizontal axis, and the variable you're measuring is on the vertical axis. Connecting the data points with a line helps us see the overall pattern, whether values are increasing, decreasing, or staying the same. One thing to watch for is the scale of the vertical axis. Sometimes graphs are designed to exaggerate or minimize trends by stretching or shrinking the axis. Always check whether the scale is evenly spaced and starts at 0 when comparing time series graphs. The shape of a distribution gives us important clues about the behavior of the data set. A distribution is symmetric when it looks roughly the same on both sides of its central peak. Many real-world data sets, like adult heights, follow this sort of pattern. A distribution is skewed right if it has a long tail on the right side. This means there are a few unusually high values. Examples include income, where most people earn less than a few very high outliers. A distribution is skewed left when the tail stretches to the left, often due to a few unusually low values. These shapes matter because they affect how we describe the data using averages and spread. A peak is a high point on a graph, showing where values are most concentrated. If there's one peak, we call it unimodal. If there are two, it's bimodal. And this often suggests the data come from two different groups, like heights of children and adults in a combined data set. Outliers are values that fall far outside the rest of the data. They may be genuine extreme values, or they might be errors, like entering 0.21 instead of 2.1 for a GPA. Either way, outliers deserve a closer look because they can distort your summary statistics and mislead your analysis. Here's a histogram showing exam scores. Ask yourself, where is the data centered? Is there one peak or multiple? Does the graph look symmetric or is it skewed? Are there bars that represent unusually high or low scores that might be outliers? Practicing this kind of visual interpretation will help you later when we begin using numerical summaries to describe data more precisely. Go ahead and pause the video and take a moment to analyze it, and then come back when you're ready and we'll talk about the solution. All right, let's take a look at the histogram. So these are a distribution of exam scores from a recent test. Right away, we can see that most of the scores fall between 65 and 95. Right in here, 65, come on, there we go, 65 to 95, right? Most of our scores are in there. The tallest bar, the peak, is in the 75 to 80 bin, right in here, this peak. That suggests that the greatest number of students scored in this range out of all of the bins. The distribution appears roughly symmetric, meaning the data is fairly balanced on either side of the central peak. That gives us a hint that the average and median scores will likely be close to each other. We can also see that very few students scored below 65, that's these two bars over here, right? Or above 95 up here. These bins are much shorter, indicating that those scores are relatively uncommon. There's no dramatic tail stretching to one side, so we wouldn't say this distribution is skewed left or right. It's pretty well centered. As for outliers, there really are no unusually low scores. If there were, this might reflect a student who had a bad test day or missed part of an exam. Notice also that we wouldn't have any unusually high scores since our distribution is already centered pretty close to the max value of scoring 100 on the test. In summary, this histogram shows a unimodal, roughly symmetric distribution with a concentration of scores in the mid-70s to mid-80s and no outliers. This is the kind of visual summary that helps us quickly assess how a group performed overall and whether there are any unusual results that need closer attention. By the way, the heights of the bars tell you how many people scored in each category. So if we add up the heights of the bars, we have our total number of test takers. So we have 2 people that scored between 55 and 60, 3 people that scored between 60 and 65, and so on. So we could just add them all up to get the total. All right, to summarize, when you're working with quantitative data, histograms, dot plots, and line charts are your most important tools. Histograms help you understand the overall shape, center, and spread. Dot plots work well for smaller data sets and make it easy to spot clusters and outliers. Line charts let you analyze how a variable changes over time. And in every case, it's important to look critically at the graph to understand its message and avoid being misled by things like axis manipulation or outliers. With these tools, you're ready to explore real-world data in a more meaningful way.